So we have the clock for the CPU that keeps track of the state. So we have fetch, decode, execute, and every time that this first light is illuminated, the CPU is supposed to get the next instruction. All of our code is going to be in memory. We're going to have about 32K of memory, and the CPU should track the memory address that it's reading from. Every time we have another cycle, the address should go up. So we fetch and then it should go up, and we fetch and it goes up. And then this is basically how a program runs. We just continue to increase some kind of counter as we execute code. And that's exactly what the instruction pointer register is, or sometimes called the program counter. So the way that I'm thinking of doing that is I have some chips here, an 8-bit memory chip, HC574. So this is going to be 8 bits of data. Now, of course, our system is going to be 16 bits. So we're going to need 2 of these, but to test it, I could use one of them. So 256, I guess we could say, addresses that can be kept track of in here. So we can start at 0 and then go to 1 and then 2 and then 3 and upwards to 255 just as one of these. But we need to be able to go upwards. So that's where this guy comes in. He's an HC283 4-bit adder. So we're going to need quite a few of these, I guess 4 of them to get to 16 bits. So he can take the input from this guy and add 1 to it and feed it back. And we can hopefully get it to increment this way. So that's the idea. I'm going to try and plug these in and get them going. I printed out the pins for them. So the 574 has 8 bits of data coming in, and then it also has 8 bits of data going out. So we can choose through, I guess, the output enable pin and the clock, when should it accept the data that we put on the data pins. And we can also output when we need it. In this case, it'll probably be outputting all the time. We're never really going to turn off the output, but we're going to be able to feed the outputs, hopefully, into the adder, which is down here. So we can feed the data already in here into the adder and then have a 1 on the adder itself. And it will hopefully combine the two, add 1 to whatever's here and put it back in. If these are zeros, then 0 plus 1 is 1, and 1 plus 1 is 2, and 2 plus 1 is 3, and just keep going up that way. So that's the idea. All right, so we have the 8 bits of data, 1 byte, we could say, and the 4-bit adder. So looking at the pins now, we need to figure out the orientation, the configuration for how we output the Q, which means output, from the register into the 4-bit adder. And then we're going to have to hardwire the other side of the addition, the other operand, to be always 1. On the adder, we have these sets of bits. We have A0, B0, so they're going to be added together and output onto the sum 0. This could be on or off, and this could be on or off, and then we'll combine them. And then we have just 4 sets of these. We have 2 operands here, output, 2 operands here, output, 2 operands here, output, 2 operands here, output. I guess like A could be what comes from the register, and then B could be our hard-coded value of just 1, like 0, 1, that will be added to get our stuff to count upwards, hopefully. So I guess we could do this one first. We have VCC here at the top right, top left, next to this little cutout. So VCC top left, I guess it's just this orientation here, and then ground is bottom right, so I'll get that connected. So for the adder, we have an A and a B for each sum. So I'm going to put the A values as the output of our register. So we need to look at that. And very simply, the outputs are right here, 1 through 8. Interesting to me that it doesn't start at 0, but I guess certain things do and certain things don't. So we know that Q1 through 4, in this case, need to go into A0 through 3. So I'm going to try and set that up. First, I should actually put in VCC and ground, then I'll go from there. Okay, so here's our ground and power. So now Q1 should go into A0. 1, 2, 3, 4, 5. So that's the top one here, going into 1, 2, 3, 4, 5. All right, the next one's gonna go into A1 right here, which is at position 3. A2 is at the top here, 1, 2, 3. And then A3 skips 1. So we have our 4 bits going into the adder. We have one side of the add-in equation, the A's. So now we need to do the B's. They're just going to be connected to power and ground. We want only the 0, I guess, to be a 1, and the rest should be zeros. 1 here, 2 is right across, and then 1, 2, 3 from the top right. All right, 1, 2, 3 is ground. So we need to ground these 2 right here. I'm out of the correct size connections, so it's not going to look very good. And then this one also needs to be grounded. Okay, so it looks a little messy, but we should have whatever is coming out of the register on one end of the equation, we could say, and then just a 1 on the other end, and it should add it together and increase that value just by 1. Now we need to take the sum, first bit, second bit, third bit, fourth bit. These need to go back into our input here so that we can get the add occur and fed back into it. So that should be lined up here very conveniently, I think. Yeah, right here, 1 through 8. So we're going to be using 1, 2, 3, 4, at least for our initial test. So sum 0 needs to go into that first slot. So 1, 2, 3, 4. My wiring is terrible, but I'll hopefully improve that as I go. Data in as well. 2 comes from the first slot here, sum 1. Sum 2 is 1, 2, 3, 4. Sum 3 is next to the end. All right, well, clearly this looks really bad, but it'll work as a prototype. So output enable should be on by default since it's inverted. So I won't touch that. And all we should need is a clock to register what's coming in. So for the adder itself, we also need to, well, for the adder, I don't think we should do anything. I think it's always adding. So why don't we connect some of the 4 outputs, since we're only using 4 bits of the adder. I think we should connect these to some LEDs, the outputs, and see what happens. Do that. I guess I'll get another breadboard. This can kind of be like our display port. I have some 1K resistors here. I'm going to take off 4 of them and just turn this into like a reusable LED indicator, because I feel like I'm going to be doing this a lot. I'm going to just stick these LEDs in here. Once our ground is connected, I think we could just plug these in and see what the values are. So I'm going to connect my ground, and then our actual outputs. We know that the outputs for the register are right here. So 1, 2, 3, 4. So we're just going to put those into the LEDs. Least significant bit down here. So our bit 0 should connect to output, I'll call it 0, but they call it output 1. Bit 1 should go to the next one. Bit 2 should go to what they call Q3. And then Q4 should go bit 3. Now we need to connect both sides to each other. So ground over here, power and share to power. We have power and ground on both sides. So now we just need to power up this guy, and then our clock signal, of course, on the chip. Can't forget about that. That's at the top right here of this chip. So we do need to share the clock there as well, which is this cable, this black cable right here. So I'm gonna borrow from here, put it into our chip right there. There's power, here is ground. So all of our lights are on now. And this actually is working pretty incredible off the bat, which is really surprising. I don't know if it's counting properly, but we're definitely doing something interesting. So I made an error here, of course. Every time I press the button, add operation seems to be taking place, and that's incorrect. We only want it to happen on this fetch cycle. So I do need to, instead of getting the clock directly from the clock signal, I need to get it from the fetch output. So let us modify that. So I'm going to pull out my clock, and you can see things floating around here, just kind of picking up floating signal, just going crazy. This is hopefully how it will look when we're ultimately running the CPU at full speed. So the clock output is somewhere down here. One of these, this resistor, that does not seem to work. Well, since it was just working, we know that maybe it's like some kind of signal issue. So let's just see, make sure it adds properly. So we're at 0 right now. We should get a 1, and we get a 3, and now we get a 6. What is that, 14? I think maybe me pressing the button is not as clean. Not really sure what is happening here. So I have been looking for a couple minutes. I noticed a couple mistakes. First of all, of course, I had my register connected directly to the clock when it really should be connected to the fetch cycle. But I tried to connect it to where the resistors are coming out, which is a mistake. I should just connect it to the actual output, not through a resistor. I'm going to connect that now to the fetch signal and then connect it to the clock. Now we should see our lights update only when the fetch light turns on. So we have an update, no updates, and then we have an update. So that works out well. The next problem is that our adder is not really working properly. So right now we have 0, and we should have a 1, only one light turn on when we reach the next fetch, but we go straight to a 3. And there's 2 different things that I'm thinking about right now. The first is that I did not tie down on this adder. There's a pin for a carry of a previous adder, which we will be using when we add more adders to this to actually make it into a 16-bit adder. So this is floating right now. I'm assuming it's adding a 1 or a 0 kind of randomly each time we pulse the latch. So I need to figure that out, what we want to do with it. It kind of seems like we could just use the carry as the 1 and not have to wire this all up the way that I did. But the biggest problem here is that first pin, and I'm sorry, I know it's very messy, but the first pin here, bottom left of the register that we have, is actually the output enable pin. And I did notice this before, but I just made a mistake when I was connecting wires. So the actual data input that we should have for our adder should be starting at the second pin, and then 4 of them. since we're just using one 4-bit adder right now. And if we look at what I did, it's really not how it should be. One of the outputs of the adder going into that output enable pin, so it's a big mistake. So a couple of things need to change here. I think the blue cable is bad. So it's our 0 and our 1 that's bad. Our blue cable should really go to that second slot, and our gray should move upwards. So maybe I could just bend it without really removing anything. We have all zeros. If we pulse to the next fetch, then nothing happens. Oh, there is some light here. So 101 is a 5. It's a little finicky. It's not really quite right. I think we should tie down the carry pin to ground. So let's just do that. Ground, fortunately, is right next door. So we have our carry in, which is really another operand really into the equation. So we need to tie this down, make sure it's a solid 0, since we already have a 1 in on our B side. So the carry in should be a solid 0 now, and let's keep pulsing our guy and see if we go up. That was a good addition right there. So right now we have, something is not right here. Sometimes the add operation does look really good. Like that was a perfect add operation. That was not. This one should still be on. Oh, my wire is out. Definitely something is up. That's a good addition right there. Oh, it's working. Maybe yeah, it's perfect so far. We have 5, we have 6, should all light up here. That's 7, 8 should be 1000, 1001 is 9, 1010 is 10 or A in hexadecimal. Awesome, this works. So it's really me pressing the button. I'm not pressing that button properly or something like that. This is wonderful. He's perfect. So we can see that our CPU, if we want to call it that, it's a little bit ambitious to call it that right now, but every time we have the fetch cycle, we are incrementing our memory. So we could just imagine that if we had a bunch of code in memory, every time our CPU goes through the fetch, decode, execute cycle, we're moving to that next level, that next position, and reading that data ostensibly is what we would be doing here, loading it from the RAM and then decoding and executing it. So this is kind of like the backbone of our execution model here, where we have the clock signal driving up a memory address, a pointer essentially, that continues to increment, and later on we'll be able to modify it by other means, like to jump around. But for now we could just have a program that runs sequentially. For example, if we look at an emulator here on the screen, we can see that as we step through the code, the instruction pointer, RIP, which is just register instruction pointer, is just continually going up by 1, and that's exactly what we're modeling here, except they can go to numbers that we can't count, but and we're only going to go to 16 bits of information, which should be, 64K. One thing, though, that I think we should change is I don't think the increment of our instruction pointer should happen when we're fetching. It should probably happen during decode. The fetch itself, I think the instruction pointer should be stable so that our instruction register can get it very cleanly. During decode, our instruction register is going to be busy doing stuff, and nobody should be caring about what he has on him. So I'm going to swap this over by 1 to make it triggered by the decode cycle. So I do need to expand this into, of course, a 16-bit version. Right now it's only 8 bytes, and we're only really adding 4 bits over and over and over. So we need 2 of these and 4 of those to make it. I'm not going to do that yet. What I want to do next is build out the memory address register that will take this data from the instruction pointer and basically tell our RAM that we need to get the instruction from that address. And then later on, I'll build this out to the full 16-bit version, just to kind of keep things going right now. So I think we'll just keep this in prototype mode. Next up, hopefully we'll put the memory address register on here that can then take the value every time we have the fetch cycle, just like we should. Every fetch cycle, it should get this data, this address from the instruction pointer, and we can simulate that we'll actually transfer it over to the memory address register and then simulate drawing that from the RAM and executing. So that's hopefully what will happen next. So thanks for joining me.